The number of faint galaxies rose steeply as detection limits improved. There was no obvious cutoff, no point at which the universe suddenly became sparse. Each time Hubble looked deeper, more galaxies appeared. This forced a rethinking of galaxy abundance. Earlier surveys had captured most of the light in the universe, but not most of the galaxies. Deep fields revealed that a large fraction of galaxies contribute very little to the total light budget. They are small, faint, and numerous. This distinction is crucial. Counting light and counting objects are not the same task. The deep-field galaxies often appeared irregular and compact, reflecting their youth. Many were undergoing intense star formation. Some would later merge into larger systems. Others would fade or be disrupted. The image was not a census of present-day galaxies alone. It was a layered record of galaxy formation across cosmic time. This introduced another layer of interpretation. When astronomers count galaxies in deep fields, they are counting galaxies as they existed at different epochs. Translating that into a present-day total requires modelling how many of those early galaxies survive as distinct systems, how many merge, and how many disappear. Extrapolation therefore becomes a multi-step process. First, the observed number density is measured. Then corrections are applied for detection limits and surface brightness dimming. Next, evolutionary models are used to connect early populations to later ones. Each step adds uncertainty. None can be skipped. This is why deep field results are not quoted as simple totals. They're expressed as ranges, often spanning factors of several. The numbers are large, but they are not precise. Even so, the paradigm shift was unmistakable. Before deep fields, it was reasonable to imagine that galaxy counts might converge to a stable value as surveys improved. After deep fields, that hope faded. The universe did not reveal a tidy endpoint. It revealed a population that kept growing as sensitivity increased. The Hubble ultra-deep field pushed this further. Even longer exposures revealed galaxies fainter and more distant than those seen before. Each improvement reinforced the same pattern. The faint end of the galaxy population was rich and extended. This did not mean that the universe contained infinite galaxies. It meant that previous counts had been incomplete in systematic ways. Deep fields also demonstrated the importance of wavelength. Optical images captured only part of the picture. Infrared observations revealed additional galaxies whose light had been stretched out of the visible range. Multi-wavelength deep fields showed that different galaxy populations dominate at different epochs. Again, the message was consistency, not chaos. The universe was structured, but that structure was layered and subtle. The deep field experiments did something else equally important. They shifted confidence from individual objects to statistical trends. No single galaxy in a deep field was especially important. What mattered was the collective behavior of thousands. This mindset aligns naturally with probabilistic counting. Deep fields do not promise completeness. They promise depth. They offer a window into populations that are otherwise invisible. The limits of extrapolation remain. A deep field cannot tell us about rare, extremely large structures. It cannot fully sample the largest voids or richest clusters. It cannot see galaxies beyond the observational horizon. But within those limits, it provides a powerful constraint. Any model of the universe that predicts too few galaxies fails immediately when confronted with deep field data. Any model that ignores faint systems collapses under their weight. The deep fields made one thing unavoidable. The universe contains far more galaxies than anyone expected when counting began. Not because the universe changed, but because the tools finally became sensitive enough to reveal what had always been there. After Hubble, galaxy counting could no longer rely on intuition shaped by brightness and prominence. It had to account for the quiet majority. That shift did not close the question of how many galaxies exist. It opened it wider, grounding it in observation while making clear that the answer would always depend on how deeply the universe was willing to be seen. Some galaxies exist at the edge of visibility. They are not small in size. In fact, some are as wide as the Milky Way itself. What makes them difficult to see is not their extent, but their faintness. Their stars are spread so thinly that the glow they produce barely rises above the background of the night sky. These are ultra-diffuse galaxies and low-surface brightness galaxies, systems that challenge almost every assumption about what a galaxy looks like. For a long time, these galaxies were effectively invisible. Traditional surveys were designed to detect concentrated light, bright cores, clear edges, distinct shapes. Diffuse systems fail on all counts. Their light is smeared across large areas of sky, making them easy to mistake for background noise, instrumental artifacts, or subtle variations in the sky itself. This is why they were missed for so long. Low-surface brightness galaxies are not rare oddities. They're common. They exist in galaxy groups, clusters, and even in relative isolation. Some contain significant amounts of dark matter. Others appear to be almost entirely dominated by it, with very few stars relative to their total mass. Their discovery forced astronomers to confront a bias that had been present all along. Peter van Dokkum played a central role in bringing these systems into focus. Using deep imaging techniques and careful data analysis, his work helped identify large populations of ultra-diffuse galaxies in environments such as the Coma Cluster. These galaxies were astonishing not because they were exotic, but because they were ordinary in number, yet extraordinary in appearance. Some of these systems span tens of thousands of light-years, comparable to large spiral galaxies, yet contain only a tiny fraction of the stars. If placed near the Milky Way, they would be obvious. At greater distances, they fade almost completely from view. This reveals a crucial point. Detectability is not governed by total luminosity alone. It is governed by how that luminosity is distributed. Surface brightness is the key quantity here. A galaxy with its stars packed tightly into a small region produces a strong signal against the background. A galaxy with the same total number of stars spread over a much larger area produces a much weaker signal, even though the total light is the same. This effect becomes severe with distance. As galaxies move farther away, their already diffuse light is further dimmed by the expansion of the universe and spread across fewer detector pixels. Eventually, the signal becomes indistinguishable from noise. Ultra-diffuse galaxies sit precariously close to this boundary even when nearby. At greater distances, they vanish entirely. This explains why early galaxy counts underestimated their numbers so dramatically. Surveys that were highly successful at detecting compact galaxies were systematically blind to diffuse ones. The universe appeared cleaner and simpler than it truly is. When detection methods improved, the picture changed. Deep imaging surveys, careful background subtraction, and targeted searches reveal that ultra-diffuse galaxies are widespread. In some galaxy clusters, they may outnumber large galaxies by significant factors. In groups, they contribute a substantial fraction of the total population. Each new detection quietly inflates the galaxy count. This inflation does not come from discovering galaxies at the edge of the observable universe. It comes from recognizing galaxies that were always there but never registered as galaxies at all. Low-surface brightness galaxies also complicate classification. Some appear to contain little or no ongoing star formation. Others host small pockets of young stars. Some are dominated by old stellar populations. Their histories vary widely. What they share is fragility. Diffuse galaxies are particularly vulnerable to environmental effects. In dense clusters, tidal forces and interactions with hot intra-cluster gas can strip away stars and gas, making these galaxies even fainter over time. Some may survive for billions of years. Others may dissolve into streams of stars, losing their identity as galaxies altogether. This again raises questions about counting. At what point does a galaxy cease to be a galaxy? When its stars are too spread out? When it loses its gas? When its surface brightness falls below detectability? Different answers lead to different totals. Luminosity bias sits at the heart of this problem. Human intuition and early instrumentation favoured bright objects. Astronomers naturally studied what stood out. What barely glowed was overlooked. This bias affects not only discovery, but interpretation. If the universe is sampled primarily through its brightest members, then those members shape expectations. Models are built around them. Counts are extrapolated from them. The recognition of ultra-diffuse galaxies disrupts that approach. It reveals that brightness is not a reliable proxy for abundance. The most common galaxies may contribute very little to the total light of the universe. They hide in plain sight, not because they are distant, but because they are faint. This has a direct impact on estimates of how many galaxies exist. If a large fraction of galaxies are diffuse, then any count based on compact systems alone will be incomplete. Even deep fields, powerful as they are, struggle to detect the most diffuse galaxies at moderate distances. Corrections must be applied. Models must assume populations that cannot be observed directly. Each assumption adds uncertainty, but ignoring these systems adds bias. There is quiet irony here. Ultra-diffuse galaxies are large. They are not small remnants or minor curiosities. They are full-scale galaxies that simply fail to shine efficiently. In a sense, they represent an alternative outcome of galaxy formation, one where dark matter dominates and star formation proceeds inefficiently. Their existence broadens the concept of what a galaxy can be. They also reinforce a recurring theme. The universe contains many more galaxies than it appears to at first glance. Not because galaxies are hiding at unimaginable distances, but because many of them emit their light reluctantly. Counting galaxies therefore becomes an exercise in humility. Each improvement in sensitivity reveals systems that challenge previous assumptions. Each new category widens the population. Ultra-diffuse and low-surface brightness galaxies ensure that the total number of galaxies continues to rise as detection methods improve. They remind astronomers that the universe does not optimize itself for visibility. It simply exists, and much of it barely glows at all. Much of the universe's structure is shaped by something that does not emit light. Galaxies form, grow, and survive inside vast concentrations of dark matter. These concentrations, known as dark matter halos, provide the gravitational scaffolding that allows gas to collect and stars to form. Without them, galaxies as we know them would not exist. Yet dark matter itself remains invisible, detectable only through its gravitational influence. This invisibility introduces a powerful complication when counting galaxies. Astronomers do not observe dark matter halos directly. They observe stars, gas, and dust, then infer the presence of halos from how those visible components move. This means that every visible galaxy is understood to be the luminous tracer of a much larger unseen structure. Halo occupation models formalize this idea. These models describe how galaxies populate dark matter halos of different masses. In simple terms, they ask how many galaxies of various types tend to live inside halos of a given size, and how those galaxies are distributed within the halo. This approach allows astronomers to connect observations to theory. Large halos tend to host large galaxies, often surrounded by smaller satellite galaxies. Smaller halos may host only one faint galaxy or none at all. By measuring galaxy clustering and comparing it to theoretical predictions, halo occupation models help estimate how many halos exist and how many of them should contain visible galaxies. This is where simulations enter the picture. Large cosmological simulations model the growth of structure in the universe from early times to the present. They track how dark matter collapses into halos, how those halos merge, and how their distribution evolves over billions of years. Baryonic processes, such as gas cooling and star formation, are then added to predict where galaxies should appear. Simon White was instrumental in developing this framework, particularly through his work on structure formation and hierarchical clustering. His contributions helped establish the idea that small structures form first and merge over time to build larger ones. In this picture, the universe naturally produces a vast number of small dark matter halos. The implication is straightforward but unsettling. If dark matter halos are abundant at small masses, then the universe should contain an enormous number of potential galaxy hosts. Yet when astronomers look around the Milky Way, they do not see nearly as many small galaxies as simulations predict. This discrepancy is known as the missing satellites problem. According to simulations, a galaxy the size of the Milky Way should be surrounded by hundreds or even thousands of small dark matter subhalos. Observationally, only a few dozen satellite galaxies are known, even after accounting for recent discoveries of ultra-faint dwarfs. At first glance, this appears to be a failure of the theory. But the issue is more subtle. The simulations predict dark matter structures, not luminous galaxies. Whether a given halo hosts visible stars depends on complex physical processes. Gas may fail to cool efficiently. Star formation may be suppressed by radiation from nearby galaxies. Supernova explosions may expel gas from shallow gravitational wells. As a result, many small halos may remain dark, containing little or no visible matter. They exist, but they do not announce themselves with starlight. This distinction is crucial for galaxy counting. If every dark matter halo hosted a visible galaxy, then galaxy counts would be dramatically higher. Instead, there appears to be a threshold halo mass below which star formation becomes inefficient or impossible. Above that threshold, galaxies form readily. Below it, halos may remain invisible. Determining where that threshold lies is an active area of research. It likely depends on environment, timing, and feedback processes. The threshold may not be sharp. It may be fuzzy, with some halos forming stars while others do not under similar conditions. This uncertainty propagates directly into galaxy estimates. When astronomers use halo occupation models to infer galaxy numbers, they must assume a relationship between halo mass and galaxy formation. Different assumptions produce different results. Some models predict many more faint galaxies than others. Observations constrain these models, but they do not uniquely determine them. The missing satellites problem has softened over time as deeper surveys have revealed more faint dwarf galaxies. The gap between prediction and observation has narrowed, but it has not disappeared entirely. Some halos likely remain completely dark. This raises a fundamental question. Should dark halos without stars be counted as galaxies? Most astronomers answer no. A galaxy, by definition, contains stars. Dark matter halos without visible components are not galaxies, even if they are structurally similar to those that host stars. This decision matters. If galaxy counts are tied to luminous systems, then invisible halos do not contribute directly. But they still shape the population indirectly, by influencing how visible galaxies form, merge, and survive. They are part of the invisible structure underlying the count. Separating inference from observation becomes essential here. Observations tell us how many galaxies we can see, corrected for known biases. Inference tells us how many galaxies likely exist below detection thresholds, based on theoretical models. These are related but not identical statements. When astronomers estimate the total number of galaxies in the observable universe, they combine both approaches. They start with observed populations. They correct for observational limits. They then use models of structure formation to estimate how many galaxies are likely missing. Each step adds uncertainty. It is important to be clear about where the data ends and where the inference begins. Observations anchor the estimates. Theory fills in the gaps. Neither can stand alone. Dark matter ensures that the universe contains far more structure than light alone reveals, but it does not guarantee that all of that structure is populated by stars. The invisible scaffolding is rich. The luminous decoration is selective. This selectivity shapes the galaxy population. In regions where conditions favor star formation, many halos light up. In harsher environments, fewer do. Over time, mergers and feedback further sculpt the population. The result is a universe where the number of galaxies is determined not only by how much structure exists, but by how efficiently that structure produces visible systems. Counting galaxies therefore becomes an exercise in restraint. One must resist the temptation to equate structure with luminosity, or to assume that every theoretical object has an observable counterpart. Halo occupation models provide a powerful bridge between theory and observation, but they do not erase uncertainty, they quantify it. The missing satellites problem illustrates this clearly. It is not a sign that something is fundamentally wrong. It is a reminder that galaxy formation is selective, environment-dependent and incomplete. Dark matter gives the universe its architecture. Light fills in parts of that architecture, leaving other regions dark. Galaxy counts reflect where the light has managed to take hold, not the full extent of what exists. Galaxies do not exist outside of time. They are not fixed objects scattered through an unchanging universe. They are processes. Each galaxy reflects a history of assembly, interaction, growth, and loss that unfolds over billions of years. This makes any attempt to count galaxies inseparable from the question of when the counting is done. The dominant framework for understanding this history is hierarchical formation. In this picture, structure builds from the bottom up. Small concentrations of matter collapse first. These early systems merge with others, forming progressively larger galaxies over time. The universe begins crowded with many small galaxies and gradually becomes populated by fewer larger ones. This framework emerged not from speculation, but from observation and simulation working together. In the early universe, galaxies were typically small, gas-rich, and highly active. Star formation rates were intense, structures were irregular, mergers were common. These early galaxies did not resemble the well-ordered spirals and smooth ellipticals familiar today. They were unstable, rapidly evolving systems. Over time, mergers reshaped them. Two galaxies colliding do not simply add their stars together. Their gas clouds compress, triggering bursts of star formation. Their orbits change, their shapes distort. Some stars are flung into extended halos or tidal streams, others settle into new configurations. Repeated over cosmic time, this process reduces the total number of galaxies while increasing their average mass. Sandra Faber played a central role in formalizing this evolutionary picture, particularly through work on galaxy scaling relations and the processes that transform star-forming galaxies into quiescent ones. Her research helped clarify how mergers, feedback, and internal dynamics drive galaxies along distinct evolutionary pathways. One of the key insights of this framework is that galaxy counts are epoch-dependent. At early times, the universe contained many more galaxies than it does now, but those galaxies were smaller and less massive. As time passed, mergers reduced their number. A present-day massive galaxy may contain the remnants of dozens or even hundreds of earlier systems. This creates an important distinction. There is the number of galaxies that exist now within the observable universe, and there is the number of galaxies that have ever existed over cosmic history. These are not the same quantity. Most galaxy counts aim to estimate the present-day number, but the data used to infer that number come from observations across time. Deep surveys capture galaxies as they existed billions of years ago. Interpreting those observations requires understanding which of those galaxies survived, which merged, and which disappeared. Some early galaxies vanish completely as independent systems. They are absorbed into larger galaxies, their stars becoming part of a new whole. Others are disrupted, stretched into streams that wrap around their descendants. Their identities are lost, even though their material persists. This disappearance is not an anomaly. It is the normal outcome of hierarchical growth. As a result, the universe becomes less crowded in terms of galaxy count, even as it becomes richer in terms of total stellar mass. Fewer galaxies, but larger ones. This time dependence complicates counting in subtle ways. When astronomers observe a deep field, they see a mixture of galaxies from many epochs. Some of those galaxies will still exist today in recognizable form, others will not. Translating observed counts into a present-day total requires models of survival and merger rates. These models depend on environment. In dense regions such as clusters, mergers are frequent. In low-density regions, galaxies may evolve more quietly. A galaxy's fate is shaped as much by where it lives as by its initial mass. This means that galaxy counts vary across cosmic environments as well as across time. A region observed at high redshift may contain many small galaxies that later merge into a handful of large ones. Another region may retain a richer population of small systems. Averaging across the universe smooths these differences, but they never vanish entirely. This introduces uncertainty that cannot be eliminated with better instruments alone. Even with perfect observations, galaxy counts would still depend on modelling how galaxies evolve. The universe does not preserve its population in a way that allows simple accounting. There is also the question of threshold. At what point in its evolution does a system qualify as a galaxy? When it first forms stars, when it reaches a certain mass, when it becomes gravitationally stable. Different answers produce different counts at early times. Early galaxies often formed stars in brief, intense bursts. Some may have flickered into existence and faded again quickly. Should such transient systems be counted? They existed, but briefly. Modern definitions typically require a galaxy to be a long-lived, gravitationally bound system. Applying that definition retrospectively to early epochs is not straightforward. Many early systems do not fit neatly. This again reinforces that galaxy counts are not timeless truths. They are contextual descriptions. Sandra Faber's work helped clarify that galaxy evolution is not a single path, but a network of possible trajectories. Some galaxies grow steadily, others are quenched early, some merge repeatedly, others remain isolated. The diversity of outcomes ensures that galaxy populations change continuously. From a present-day perspective, the universe contains a certain number of galaxies above certain thresholds of mass and brightness. That number reflects the outcome of billions of years of mergers, disruptions, and survivals. From an earlier perspective, the universe contained many more galaxies, but fewer large ones. Both statements are correct. They describe different moments in the same unfolding process. This time, dependence places a natural limit on precision. Any number quoted without reference to epoch is incomplete. The question how many galaxies are there must always be accompanied by when. Most often, the implicit answer is now, within the observable universe. But even that now is inferred from light that left galaxies at different times. Counting galaxies, therefore, becomes an exercise in temporal translation. Observations made across billions of years are stitched together into a present-day estimate using models of evolution. Those models are well constrained in broad terms, but not exact in detail. They capture trends, not individual histories. The result is a range, not a point. Understanding galaxy counts requires accepting that the universe does not keep a ledger. It builds, dismantles, and rebuilds its structures continuously. What exists at one moment is the residue of countless earlier configurations. Galaxies are not conserved entities. They are temporary arrangements of matter and energy shaped by gravity and time. Recognizing this shifts the focus away from seeking a single final number. Instead, it invites a deeper appreciation of how abundance itself evolves. The universe has not always contained the same number of galaxies, and it never will again. Any answer to the question of how many galaxies exist is therefore a snapshot, framed by time, shaped by history, and provisional by nature. That does not make the question meaningless, it makes it honest. At a certain point, the universe becomes too large to observe directly in full detail. No telescope can watch billions of galaxies form, merge, and evolve across cosmic time. No survey can capture every faint system, every interaction, every moment of transformation. To understand how a universe full of galaxies behaves as a whole, astronomers turn to a different tool. They build a universe instead. Large cosmological simulations attempt to recreate the evolution of structure from the earliest moments after cosmic expansion began to the present day. They begin with simple initial conditions, guided by observations of the early universe, and allow gravity, expansion, and physical laws to shape what emerges. These simulations do not draw galaxies by hand. They allow them to form naturally from the collapse of matter under gravity. The backbone of these simulations is dark matter. Vast numbers of simulated particles represent the distribution of dark matter across space. As the simulation evolves, these particles clump together, forming halos, merging, and creating the large-scale web of structure seen in galaxy surveys. Once this dark matter framework is in place, ordinary matter is added. Gas flows into halos, it cools, it collapses, stars begin to form. Over time, galaxies emerge within the simulated universe. Volker Springel has been a central figure in developing these computational approaches, particularly through large-scale simulations that combine dark matter dynamics with models of galaxy formation. His work helped demonstrate that it is possible to reproduce many of the statistical properties of the observed universe using physically motivated rules. These simulations are not small. They often track billions of particles across volumes hundreds of millions of light-years wide. They require vast computational resources and months of processing time. Each run produces enormous datasets that must be analysed carefully. Despite their sophistication, these simulations face an unavoidable limitation. They cannot resolve everything. The processes that govern star formation, supernova explosions, black hole growth, and gas turbulence occur on scales far smaller than the resolution of even the largest simulations. It is not possible to calculate these processes from first principles at every point in the simulated universe. Instead, simulations rely on what are known as subgrid models. Subgrid models describe how small-scale physics behaves on average within a larger region. They are informed by detailed observations and smaller simulations, but they remain approximations. They specify, for example, how efficiently gas turns into stars under certain conditions, or how much energy a supernova injects into its surroundings. These choices matter. Changing a subgrid prescription can alter the number of galaxies that form, their sizes, their brightness, and their survival rates. Small changes at the microscopic level can ripple outward, reshaping the macroscopic population. This introduces a fundamental humility into simulation-based counting. When a simulation predicts a certain number of galaxies above a given mass or brightness, that number reflects both the underlying physics and the assumptions embedded in the model. Agreement with observation is meaningful, but it is not absolute proof. Disagreement is informative, but not necessarily failure. What matters is the pattern. Modern simulations successfully reproduce many large-scale features of the universe. They match the clustering of galaxies. They reproduce the distribution of galaxy masses. They capture the emergence of filaments, voids, and clusters. When simulations and observations agree on these broad trends, confidence grows that the underlying framework is sound. At the same time, tensions remain. Some simulations predict more small galaxies than are observed. Others struggle to reproduce the correct number of massive galaxies at certain epochs. The precise balance between star formation and feedback remains an active area of refinement. These tensions are not embarrassing. They are productive. They highlight where understanding is incomplete. They point to physical processes that may be missing or misrepresented. They guide new observations and motivate improved models. From the perspective of galaxy counting, simulations serve a specific role. They provide a way to estimate populations that cannot be observed directly. They suggest how many galaxies should exist below detection thresholds. They predict how galaxy numbers should change with time and environment. But they do not replace observation. A simulated galaxy is not a detection. It is a hypothesis about what should exist, given a set of assumptions. Observations test those hypotheses. When the two diverge, the assumptions are revisited. This back and forth between simulation and observation is central to modern cosmology. It ensures that galaxy counts are not extrapolated blindly. They are constrained by data at every step. Simulations are adjusted until they reproduce what is seen, and then used cautiously to explore what is unseen, there's also a deeper lesson here. Simulations reveal that the universe naturally produces complexity. Even with simple initial conditions and well-understood laws, the outcome is rich, varied, and sensitive to small changes. Galaxy populations are not fine-tuned to simplicity. This reinforces why galaxy counts resist precision. The universe does not contain a neat, evenly spaced collection of galaxies. It contains a hierarchy of structures shaped by chance encounters, feedback loops, and environmental effects. Simulations capture this messiness, not eliminate it. When astronomers quote estimates for the total number of galaxies, they often rely on simulations to fill in the faint end of the population. But they do so with caveats. The numbers are conditional. They depend on how star formation behaves in low-mass halos. They depend on feedback efficiency. They depend on how galaxies respond to their surroundings. All of these dependencies are areas of ongoing research. Volker Sprengel and others have emphasized that simulations are tools for understanding, not oracles. They help explore possibilities. They clarify relationships. They expose sensitivities. They also remind us of limits. No simulation can capture every detail. No model can include every process at full resolution. There will always be uncertainty at the smallest scales, and those uncertainties will propagate upward. This does not undermine the value of simulations, it defines it. By comparing simulated universes to the real one, astronomers learn which assumptions are reasonable and which are not. They learn where confidence is warranted and where caution is required. In the context of galaxy counting, simulations provide a vital complement to observation. They help bridge the gap between what can be seen and what likely exists, but they do not deliver a final number. Instead, they reinforce a pattern that has emerged again and again. Every time the universe is examined with greater depth or broader scope, it reveals more structure than expected. Not because it is deceptive, but because it is generous. Simulating a universe full of galaxies does not simplify the counting problem, it deepens it. And in doing so, it reminds us that understanding abundance is less about reaching closure and more about refining perspective, one assumption at a time. At some point, the question stops being how many galaxies exist in principle and becomes how many can actually be observed today. This distinction matters. The observable universe is not defined by imagination or theory, but by light that has had time to reach us, and by instruments capable of detecting it. Within those limits, astronomers attempt to estimate how many galaxies are present right now, acknowledging that any answer is provisional and conditional. Modern observational studies tend to converge on large ranges rather than single numbers, depending on how faint a system must be to qualify as a galaxy, and how aggressively corrections are applied for unseen populations. Estimates for the number of observable galaxies typically span from hundreds of billions to several trillion. This spread is not a sign of disagreement about basic facts. It reflects methodological differences. Some surveys focus on counting galaxies directly detected in deep imaging, then extrapolate cautiously to account for incompleteness. Others incorporate results from simulations, halo occupation models, and luminosity functions to infer how many galaxies likely exist below detection thresholds. Each approach rests on different assumptions about galaxy formation, survival, and detectability. Christopher Consolis has been central in synthesizing these approaches, combining deep field observations with statistical corrections to estimate the total number of galaxies within the observable universe. His work emphasized that earlier counts had dramatically underestimated galaxy abundance by missing faint, small, and diffuse systems. One of the key insights from this synthesis is that sensitivity drives the count. As telescopes become more sensitive, they do not simply refine existing numbers, they reveal entirely new populations. Each improvement in depth uncovers galaxies that were previously invisible, especially at the low mass and low surface brightness end of the population. This creates a predictable pattern. Galaxy counts rise as surveys deepen. They do not plateau cleanly. The reason lies in the shape of the galaxy luminosity function. Bright galaxies are rare, faint galaxies are common. The number of galaxies increases steeply as intrinsic brightness decreases. Missing even a small range at the faint end can remove a vast number of galaxies from the count. Early surveys captured most of the light in the universe, but not most of the galaxies. Modern surveys push deeper, capturing more of the population, but still not all of it. Different surveys also probe different wavelengths. Optical surveys excel at detecting galaxies with active star formation. Infrared surveys reveal dust-obscured and high redshift systems. Radio observations trace gas-rich galaxies that may be faint in visible light. No single survey captures the full diversity. Combining these datasets requires careful cross-calibration. Objects detected in one wavelength may be missed in another. Selection functions differ. Corrections must be applied consistently. Even then, uncertainty remains. Cosmic variance plays a role. A deep field may sample a region that is slightly overdense or underdense compared to the cosmic average. Large area surveys reduce this effect but cannot eliminate it entirely. There is also the issue of classification. Some faint systems sit near the boundary between galaxies and star clusters. Including or excluding them changes the count. Reasonable researchers can make different choices without error. When modern studies quote numbers on the order of a few trillion galaxies, they are not claiming to have counted each one. They are stating that given current observations and models, this is the most plausible range for how many galaxies exist within the observable universe today. The phrase "within the observable universe" is doing important work here. It excludes galaxies beyond the observational horizon, which cannot be seen or counted directly. It also excludes dark matter halos without stars, which are not classified as galaxies under standard definitions. Within those bounds, the uncertainty is not trivial, but it is constrained. The lower end of estimates corresponds to conservative assumptions about the faint end of the galaxy population. The higher end assumes that many small and diffuse galaxies remain undetected, even in the deepest surveys, consistent with simulation predictions and local group studies. What is striking is not the exact number, but the scale. Even the most conservative modern estimates place the number of observable galaxies far above what was imagined a century ago. The universe is not sparsely populated with a few majestic systems. It is crowded with vast numbers of modest ones. This conclusion is robust across methods. Whether one starts from deep field counts, luminosity functions, or simulation-informed corrections, the same qualitative picture emerges. Galaxies are abundant, faint galaxies dominate the numbers, detectability, not existence, sets the limits. This is where conditional certainty comes in. Astronomers are confident about trends, distributions, and orders of magnitude. They are less confident about exact totals. That imbalance is appropriate. The data support broad conclusions, not precise inventories. When the number changes from hundreds of billions to trillions, it is not because earlier work was wrong. It is because new sensitivity reveals new populations, forcing revisions. This process will continue. Future telescopes will push detection limits further. New surveys will reveal galaxies even fainter and more diffuse than those known today. Counts will rise again, not because the universe has changed, but because the view has improved. So how many galaxies can be observed today? The honest answer is a range, not a figure. A range grounded in observation, constrained by theory and shaped by detection limits. Within the observable universe, there are at least hundreds of billions of galaxies, and very likely many times that number. The exact total depends on how faint one is willing and able to look. That uncertainty is not a weakness. It is a reflection of how the universe presents itself. The universe is generous with structure, but selective with visibility. And every time sensitivity improves, it reminds us that abundance was never the limiting factor. Only perception was. The arrival of the James Webb Space Telescope did not rewrite the story of galaxy counting. It sharpened it. From the beginning, Webb was designed to see what earlier telescopes could not. Its strength lies in infrared sensitivity, allowing it to detect light that has been stretched far beyond the visible range by cosmic expansion. This makes it especially powerful for observing distant galaxies, whose light began its journey when the universe was young. Before Webb, much of the early universe was inferred rather than seen. Galaxies at very high redshift were detected only in small numbers, often near the limits of confidence. Their properties were uncertain. Their abundance was extrapolated cautiously. Webb changed the balance of evidence. By observing in the infrared with unprecedented sensitivity and resolution, Webb revealed galaxies that had previously slipped below detection thresholds. Many of these systems are faint, compact, and surprisingly numerous. They appear at epochs when the universe was only a few 100 million years old, a period once thought to be sparsely populated with galaxies. These early observations did not come from a single dramatic image or headline result. They emerged from careful analysis by multiple research teams working independently, comparing data across fields, calibrating measurements, and testing assumptions. The emphasis was not on spectacle, but on consistency. What these teams found was not chaos, but continuity. The early universe appears rich in small galaxies, just as models of hierarchical formation predict. Webb did not suddenly reveal a universe overflowing with unexpected giants. Instead, it filled in the faint end of the population, revealing systems that were always expected to exist, but had not yet been observed directly. This matters for counting. Webb does not allow astronomers to count all galaxies directly. It does not eliminate observational horizons. It does not bypass surface brightness dimming. What it does is tighten constraints. It reduces the gap between what is observed and what is inferred. By detecting galaxies at earlier times and lower luminosities, Webb improves estimates of how many galaxies formed in the early universe. Those estimates, in turn, inform models of how many galaxies survive to the present day, and how many merge or disappear along the way. The revisions are indirect but significant. When Webb reveals that faint galaxies are more common at high redshift than previously measured, it suggests that earlier surveys underestimated early galaxy abundance. That does not automatically increase the present-day count, but it changes the inputs used to model galaxy evolution. More early galaxies imply more mergers, more hierarchical growth, and potentially more remnants embedded in today's massive galaxies. It also implies that some early galaxies may persist as faint systems today, contributing to the low luminosity population. Webb also clarifies the role of wavelength in detection. Many early galaxies emit most of their light in ultraviolet wavelengths due to intense star formation. By the time that light reaches Earth, it has shifted into the infrared. Optical telescopes simply could not see it. This does not mean those galaxies were invisible in principle. They were invisible to certain instruments. Webb's infrared vision reveals a population that bridges the gap between theory and observation. It confirms that early galaxy formation was efficient and widespread, not rare or exceptional. At the same time, Webb reinforces familiar limitations. Even with its sensitivity, Webb observes only small regions of sky in extreme depth. It does not provide an all-sky census. Cosmic variance remains a concern. Some deep fields appear richer than others. Statistical interpretation is still required. Webb's discoveries therefore feed into the same probabilistic framework established by earlier surveys. They do not replace it. The difference lies in confidence. With Webb, astronomers are less reliant on extrapolation alone at high redshift. They can measure luminosity functions more directly. They can observe the shapes, sizes, and stellar populations of early galaxies rather than inferring them from faint smudges. This reduces uncertainty at one end of the problem while leaving other uncertainties intact. Webb has also revealed that some early galaxies are more massive and more chemically evolved than expected at their observed epochs. These findings sparked initial surprise, but careful analysis showed that they remain consistent with revised models of rapid early star formation, rather than requiring a fundamental rethinking of cosmology. This pattern is instructive. Webb does not overturn existing frameworks, it refines them. It exposes where assumptions were conservative. It highlights where models need adjustment, not abandonment. For galaxy counting, this means that estimates continue to rise at the margins rather than jumping discontinuously. The universe revealed by Webb is richer, but not alien. There is an important psychological shift here. Public discussion often frames new telescopes as revolution machines, poised to demolish old ideas. In practice, progress is more incremental. Webb's results sit comfortably within the trajectory established by deep fields, simulations, and statistical surveys. Each new population discovered was anticipated in some form. Webb simply makes it visible. This continuity matters because it reinforces trust in the methods used to estimate galaxy abundance. When new instruments confirm rather than contradict the broad picture, confidence in the underlying framework grows. The broad picture is this: galaxies are numerous. Faint galaxies dominate by number. Early galaxies were abundant, many merged, some survived. Detection limits, not existence, set the boundaries of observation. Webb strengthens every part of that picture. It does not answer the question of how many galaxies exist with finality. It narrows uncertainty. It improves calibration. It reveals populations that push counts upward in controlled ways. Future analyses will incorporate Webb's data into luminosity functions, merger histories, and halo occupation models. Estimates will be revised again. The numbers may increase. The ranges may tighten, but the character of the answer will remain the same. There will still be a range rather than a point. There will still be assumptions. There will still be galaxies below detection thresholds. What Webb changes is not the nature of the uncertainty, but the scale of confidence. The universe appears once again to be generous with galaxies and consistent with its own history. Webb does not close the book on galaxy counting. It adds more pages, written in finer detail, without changing the story's direction, and that is perhaps its most important contribution. It shows that deeper vision does not simplify the universe. It reveals it more fully, while preserving the quiet truth that no matter how far instruments reach, some structure will always remain just beyond the edge of sight. There comes a point where the question is no longer about what has been missed, but about what can never be seen. Not because telescopes are insufficient or surveys incomplete, but because the structure of the universe itself sets limits on observation. These limits are not technological. They are causal. The universe has a finite age and light travels at a finite speed. Together, these facts define a boundary known as the cosmic horizon. It marks the greatest distance from which light has had time to reach us since cosmic expansion began. Anything beyond that boundary has not yet had the opportunity to communicate its existence. This horizon is not an edge in space. It is an edge in time. Galaxies beyond it may exist. They may be numerous. They may resemble the galaxies we see nearby, or differ in ways that cannot be tested. What matters is that their light has not arrived, and may never arrive, no matter how long one waits. This introduces an important distinction. Some galaxies are unseen because they're too faint, too diffuse, or too distant for current instruments. These galaxies are unseen, but not unreachable. With better sensitivity, longer exposures, or different wavelengths, many of them can be revealed. Other galaxies are unreachable. They lie beyond the causal horizon in regions of space whose light has not reached Earth, and whose future light may never do so, depending on the continued expansion of the universe. These regions are not hidden behind dust or noise. They are separated by the structure of space-time itself. This distinction matters deeply for how galaxy counts are interpreted. When astronomers estimate how many galaxies exist, they're careful to specify that the count applies to the observable universe. This is not a philosophical caveat, it is a physical constraint. The observable universe is the portion of the cosmos that can, in principle, be studied using light or other signals. Beyond it lies more universe, but not more data. It is tempting to ask what lies beyond the horizon. It is also tempting to extrapolate. If the observable universe contains hundreds of billions or trillions of galaxies, then perhaps the unobservable regions contain more of the same. This may be true, but science proceeds cautiously here. The laws of physics appear consistent across the observable universe. Large-scale structure shows statistical uniformity when averaged over vast distances. These observations support the idea that regions beyond the horizon are not fundamentally different. Even so, this remains an inference, not an observation. There is a critical difference between extending a pattern within observed data and claiming certainty about what lies forever beyond reach. The former is a controlled assumption. The latter is speculation. For this reason, astronomers avoid statements about the total number of galaxies in the entire universe. They restrict themselves to what can be observed, modelled, and constrained by data. This restraint is not a lack of imagination, it is methodological discipline. Causal horizons also evolve over time. As the universe ages, light from more distant regions reaches us. The observable universe grows. Galaxies that were once beyond reach become observable, not because they moved closer, but because time has allowed their light to arrive. At the same time, cosmic expansion introduces a competing effect. Some regions of space are receding so rapidly that light emitted today will never reach us in the future. Those regions lie beyond what is sometimes called the event horizon. They are not merely unobserved, they are permanently inaccessible. This creates a subtle asymmetry. The observable universe grows, but not without limit. There are regions that will remain forever outside our observational domain. Galaxies within those regions cannot be counted, catalogued, or confirmed. They are not missing data points. They are inaccessible in principle. This is why careful discussions of galaxy abundance stop where observation stops. They do not invoke infinity. They do not speculate freely beyond causal limits. They acknowledge what is known, what is inferred, and what is fundamentally unknowable. This approach preserves clarity. Unseen galaxies within the observable universe represent an incomplete census. They motivate deeper surveys, better instruments, and improved models. Unreachable galaxies lie in a different category altogether. They do not motivate better observation. They motivate humility. It is also important not to conflate size with reach. The observable universe is vast. Its diameter spans tens of billions of light years. Within it, there is room for extraordinary numbers of galaxies. The fact that some regions are beyond reach does not diminish the richness of what can be studied, nor does it imply that the observable universe is atypical. All available evidence suggests that the observable universe is a fair sample of the larger whole, at least in statistical terms. But this remains an assumption grounded in observation, not a demonstrable fact about everything that exists. Avoiding infinity claims is part of this discipline. Statements about infinite numbers of galaxies sound impressive, but they do not arise from measurement. They arise from extrapolating beyond the domain where evidence applies. In science, such statements are treated with caution. The universe may be infinite. It may be finite but unbounded. It may have a structure that does not conform neatly to either category. Current observations cannot decide this question conclusively. What can be said with confidence is this. Within the observable universe, there are vast numbers of galaxies, far more than early astronomers imagined. Their abundance is supported by multiple independent lines of evidence. Their diversity is well established. Their distribution follows understandable patterns shaped by physics and time. Beyond the observable universe, there is silence, not emptiness, but absence of information. This silence is not frustrating, it is clarifying. It draws a boundary around what science can responsibly address. It reminds us that some questions do not have answers because they do not have access. Counting galaxies, therefore, is not about reaching for the absolute. It is about describing what can be known within the limits set by nature itself. The observable universe offers more than enough complexity to occupy generations of inquiry. Beyond it lies a continuation that may never be tested. Maintaining that distinction allows galaxy counts to remain grounded, meaningful, and honest. It also reframes the original question: how many galaxies are there? Within reach, the answer is vast, conditional, and improving. Beyond reach, the only correct response is restraint, and in that restraint there is a quiet strength. At the end of all the surveys, simulations, and revisions, the number itself can begin to feel misleading. Hundreds of billions, trillions, vast quantities that stretch language until it starts to lose its grip. It is tempting to treat these figures as answers, as if the goal of the exercise were to land on a single, authoritative total. But that has never really been what galaxy counts are for. The number does not represent a final inventory. It represents a description. Every estimate of how many galaxies exist is inseparable from the method used to obtain it. Change the depth of a survey, and the number changes. Change the wavelength and the number changes again. Adjust the definition of what qualifies as a galaxy and the total shifts, sometimes dramatically. This is not a flaw in the process. It is the process. Galaxy counts are method-dependent descriptors. They summarize what a particular combination of instruments, assumptions, and corrections reveals about the universe. They are statements about visibility, classification, and inference, not declarations of absolute fact. This is why ranges replace exact totals. When astronomers report that there are likely between hundreds of billions and several trillion galaxies within the observable universe, they are not hedging. They are being precise in the only way the problem allows. The range captures uncertainty that cannot be eliminated without pretending to know more than observation permits. Exact numbers imply closure. Ranges acknowledge limits. Those limits are not just technological, they are epistemic. There are limits to what can be known, even in principle, about a universe observed from one location, at one moment in time, using light that arrives with delays measured in billions of years. Some galaxies are faint enough to escape detection. Some lie in regions of space that will never be observed. Some existed only briefly before merging into larger systems. No amount of improved instrumentation can fully erase these constraints. This does not mean knowledge is shallow. It means it is conditional. Galaxy counts depend on definitions of galaxies, on models of evolution, on corrections for what cannot be seen, and on assumptions about what lies just beyond detection thresholds. Each of these elements is grounded in evidence, but none is exact. Together they produce a picture that is robust in scale and structure, even if imprecise in detail. That robustness is the point. The value of galaxy counts lies not in the last digit, but in the order of magnitude. Not in whether the number is 2 trillion or 3 trillion, but in the recognition that the universe is extraordinarily rich in structure. A century ago, the number of known galaxies was 0. A few decades later, it was measured in dozens, then thousands, then millions. Each increase reflected not a changing universe, but a changing view. Today's numbers continue that trajectory. They tell us that galaxies are not rare, isolated islands. They are the dominant units of visible structure in the cosmos. They populate space densely at small scales, even as vast distances separate them at large scales. They also tell us something quieter, that the universe does not yield to enumeration in the way everyday objects do. It resists being totaled cleanly. Every attempt to count reveals new categories, new edge cases, new subtleties that complicate the picture. Precision gives way to perspective. This shift can feel unsatisfying if the expectation is a single, definitive answer, but it becomes deeply satisfying when the goal changes from certainty to understanding. The number of galaxies is not a score to be settled. It is a summary of how observation, theory, and limitation intersect. When astronomers revise estimates upward, They're not correcting mistakes so much as incorporating previously unseen structure. When they quote uncertainty, they are not admitting ignorance so much as respecting the boundary between data and assumption. In this sense, galaxy counts function as a mirror. They reflect the reach of instruments. They reflect the maturity of theory. They reflect how carefully uncertainty is handled. They even reflect philosophical restraint, the decision to stop where evidence stops. Scale matters more than precision here. Whether the observable universe contains hundreds of billions or several trillion galaxies, the implication is the same. The cosmos is populated on a scale that overwhelms intuition. It contains far more structure than can be held comfortably in mind, even when reduced to numbers. And yet those numbers are meaningful. They anchor imagination. They constrain models. They remind us that the Milky Way is one among an immense population, not a central fixture. What the number really represents, then, is not an answer to a counting problem, but a statement about abundance under constraint. It says that within the limits of what can be observed, corrected, and responsibly inferred, the universe is lavish with galaxies. It also says that certainty has a boundary, and that science is strongest when it marks that boundary clearly, rather than pretending it does not exist. As the discussion draws toward closure, that perspective matters more than any figure. The question of how many galaxies there are does not resolve into a tidy conclusion. It resolves into an appreciation of scale, method, and limit. And in that resolution, something important happens. The universe becomes neither fully known nor fundamentally mysterious. It becomes intelligible in parts, bounded in others, and open to continued refinement. That balance, more than any number, is what the count ultimately represents. Counting galaxies has never been a task with an endpoint. From the moment astronomers realized that the Milky Way was only one system among many, the act of counting became inseparable from discovery itself. Each improvement in observation changed not only the number, but the meaning of the number. What began as a question of how many objects could be seen slowly became a question of how scientific knowledge grows. Counting in this context is not bookkeeping. It is an evolving scientific process. At every stage, galaxy counts have reflected the tools available, the definitions in use, and the assumptions considered reasonable at the time. Early counts were shaped by naked eye observations and photographic plates. Later counts depended on digital detectors, statistical surveys, and computational models. Today's estimates draw on infrared telescopes, deep fields, simulations, and carefully quantified uncertainty. At no point has the universe offered a final answer. Instead, it has offered partial views that improve gradually, sometimes unevenly, as methods advance. What changes is not just how many galaxies are thought to exist, but how confidently different parts of the population can be described. This is why a revision is not a weakness of galaxy counting. It is its defining strength. When estimates rise, it does not mean earlier astronomers were careless or mistaken. It means they were working honestly within the limits of their evidence. As those limits expanded, so did the count. Each revision records progress rather than failure. Humility is built into this process. Astronomers are careful to distinguish between what is observed directly and what is inferred statistically. They separate detectable galaxies from predicted populations. They acknowledge that some systems will always remain below detection thresholds, while others lie beyond causal reach altogether. This restraint is not pessimism, it is precision. Scientific counting advances by marking boundaries clearly. It does not blur the difference between evidence and extrapolation. It does not claim completion where none exists. There is also continuity in this process. Modern galaxy counts, for all their sophistication, still rest on the same basic principle that guided early work. They begin with the Milky Way. Distances are calibrated locally. Galaxy types are understood by comparison with nearby examples. The structure of the local group informs models applied across cosmic volumes. In this sense, the counting always returns home. Even now, uncertainties in the Milky Way's mass, extent, and satellite population influence broader estimates. Discoveries of new dwarf galaxies nearby still alter expectations for what might exist elsewhere. The nearest galaxy remains a reference point, not a solved problem. This circularity is not a flaw, it is a reminder that knowledge is anchored. The universe is not surveyed from the outside, it is studied from within one galaxy, at one moment in time, using signals that arrive late and incomplete. Every count carries that perspective with it. Seen this way, galaxy counting becomes less about totals and more about process. It is a dialogue between observation and theory. Surveys reveal patterns, models attempt to explain them, discrepancies prompt refinement, new instruments reopen questions that seem settled. Numbers shift, not randomly, but in response to improved understanding. There is no expectation that the process will end. Future telescopes will detect fainter galaxies. New surveys will explore wider areas with greater sensitivity. Simulations will incorporate more detailed physics. Definitions may evolve again as new classes of objects blur existing categories. Each step will add structure, not closure. This openness is not unsettling, it is stabilizing. It ensures that conclusions remain proportional to evidence. It prevents numbers from hardening into dogma. It keeps the science responsive rather than rigid. In everyday life, counting implies completion. Once all objects are tallied, the task is finished. In cosmology, counting is different. The act of counting exposes new layers of complexity that make further counting necessary. The universe does not resist being understood, but it does resist being finalized. Ending where the story began brings this into focus. The Milky Way still arcs across the night sky as a faint band of light. It still feels singular from the inside. It still hides parts of itself behind dust, distance, and dark matter. Even here, completeness remains out of reach. And yet, from that imperfect vantage point, astronomers have inferred a universe filled with galaxies beyond imagination. Not through certainty, but through careful accumulation of evidence. Not through final answers, but through a process that refines itself over time. Counting galaxies, then, is not about pinning down the universe. It is about learning how to ask large questions responsibly, how to revise answers without embarrassment, and how to remain grounded while dealing with scales that exceed intuition. The universe, in this sense, remains unfinished, not because it is incomplete, but because understanding it is an ongoing activity rather than a destination. The numbers will continue to change, the methods will continue to improve, the picture will continue to sharpen at the edges. What remains constant is the approach. Careful observation, explicit limits, willingness to revise, respect for uncertainty. That is what galaxy counting ultimately represents. Not a final tally of what exists, but a record of how far understanding has come, and a reminder that even at cosmic scales, knowledge advances one measured step at a time. The Milky Way turns quietly within a vast population of galaxies, none of them fully counted, all of them part of a universe that does not demand completion in order to be understood. And in that unfinished state, the science remains both grounded and open, exactly where it needs to be. There is now no serious doubt about the broad picture. Galaxies are not rare features scattered thinly across space. They are the primary units of visible structure in the universe. They form wherever matter collects inside dark matter halos. They grow, merge, fade, and sometimes disappear. They populate the observable universe in extraordinary numbers, far beyond what early astronomy ever imagined. That much is firmly established. What has also become clear is why no final number exists. Every method used to count galaxies depends on limits of sensitivity, limits of resolution, limits imposed by distance, time, and the expansion of space itself. Even definitions matter. What qualifies as a galaxy at one scale or epoch may blur into something else at another. These are not temporary obstacles waiting to be removed by better technology. They are structural features of how the universe can be known from within. Uncertainty, in this context, is not a failure to decide. It is an honest reflection of the problem's shape. When astronomers quote ranges rather than totals, they are not avoiding commitment. They are committing to evidence rather than impression. They are stating clearly where observation ends and inference begins. They are choosing accuracy over false precision. This is appropriate, not disappointing. Because what matters most is not the last digit, but the scale. The universe contains at least hundreds of billions of galaxies within the observable region, and very likely many more. Faint galaxies dominate the population. Large luminous galaxies like the Milky Way are impressive, but statistically uncommon. Most galaxies are small, dim, and easily missed unless observation is pushed to its limits. That conclusion holds across methods. It holds whether one starts from nearby dwarf galaxies, deep field surveys, statistical corrections, or cosmological simulations. It holds whether one looks backward in time or outward in space. It holds whether one counts directly or infers carefully. Galaxies are common. They are the ordinary outcome of cosmic structure formation, not rare accidents. Wherever conditions allow matter to collapse and cool, galaxies tend to appear. The universe does not produce a few masterpieces. It produces an abundance of modest systems. This abundance reshapes perspective. From inside a single galaxy, space feels vast and empty. Stars are separated by immense distances. Other galaxies appear remote, faint, and sparse. Yet when viewed statistically, the universe is crowded at small scales, dense with structure that only thins when distances become enormous. This contrast between experience and reality is one of astronomy's quiet lessons. Another is restraint. There is a natural temptation to ask for a final answer, a single number that resolves the question once and for all. But the universe does not cooperate with that expectation.